Hey guys, so today in lecture I got a question about question 77 on page 275 of your textbook. This is an optimization problem about Snell's law. So let's go through the question. The question is asking is basically here's what the question says. So you're saying let v1 be the velocity of light in air and v2 is the velocity of light in water, okay? And then according to Fermat's principle, we're telling you that a ray of light travels from a point A in the air to a point B in the water by a path that minimizes the time taken. This is important to note. Minimizes the time taken. Okay. We want to show that this relationship holds. Where theta 1 is the angle of incidence of the incoming light, and theta 2 is the angle of refraction of the light that's refracted in the water. Okay. So let's get to proving Snell's law. All right. So first of all, whenever you're dealing with an optimization problem, there's a few things you have to do. First thing to do is draw a graph, draw a picture. Fortunately, they've already drawn a picture for us here. The other thing we can do is right now, what do we want to minimize? We want to minimize time. Okay, so let's just keep this in mind. This relationship in mind. This is an important relationship to keep in mind. Just as a refresher, I'm sure you guys already know this, but v equals t over d, right? So t equals d over v. It's going to be important to keep in mind. Okay, now let's get to labeling our variables. Okay, we're going to label every inch of this picture. Basically, when you have the light moving through the air, so first of all, we can tell that Snell's law, is true, right? Because when the light is in the air, it takes it takes a longer path than when it's in the water, right? Because it can move faster in the air than when it's in the water. So we can tell too from the picture that the relationship is true there. So basically, what are our variables here? What are the important variables? Okay, so when the light is in the air, it travels this distance here, right? It travels this distance here. This is the distance that the light in the air travels. Let's call this h1, okay? Hypotenuse 1. Okay, this is a right angle, and then in the water, same thing. This is the distance that the light travels in the water. Let's call this h2, hypotenuse 2. All right, okay, we'll call this height of the triangle A. We'll call this height of the triangle B. And now let's get to labeling the bases of both of these right angled triangles. So here's something you can do. You can say, okay, this is x1 and this is x2. You could do that, sure. But the idea is you want to reduce the amount of variables here, okay? So if you can find a variable that can be described in terms of another variable, you want to eliminate redundancy, right? You want to have as few variables as possible while still capturing all of the information you need about the question. So instead of doing something like this, we can say, okay, this distance here, let's call this x1, okay? Let's call this entire distance L, or let's just call this x, actually, not x1. We don't need to call it x1. So then we can call the base of this triangle L minus x, right? That makes sense. And so now instead of introducing, two different variables, we have one variable and, a constant, okay? Great. All right. So now let's get to writing our equations. What are we trying to minimize? We are trying to minimize t, right? We're minimizing t total, okay? T total is the total time it takes for light to make this journey from A to C to B. So T total is going to be equal to the time it takes for it to travel in the air. I'll call this T1, plus the time it takes for it to travel in the water. I'll call this T2. And so just to be clear, this is how long it takes for it to go from A to C, and this is A to B. My mistake. A to C. I was right the first time. A to C, and then this is how long it takes for it to travel from C to B. Okay, and of course we know that it travels through air with a velocity v1, and travels through the water with a velocity of v2, which is smaller than v1. Okie dokie. Well, let's figure out what T1 and T2 are. What's T1 going to be equal to? Distance over speed, right? What's the distance that it travels? h1. So T1 equals h1 over v1. And T2, conversely, equals h2 over v2. Okay, great. So again, as I mentioned, we ideally want to reduce the amount of variables that we're dealing with as much as we can. So let's put h1 in terms of other variables, okay? And the other variable that we're going to be putting it in terms of is x, right? That's the only other variable here. A and b, we can sort of ignore, or we can sort of consider it to be constants. So here, h1 in terms of a and x, well, that's just a squared plus x squared over v1. And then h2 over v2, well, h2, that's just square root of b squared. Let's see if we can write that properly. B squared plus L minus X squared divided by V2. Okay, great. So now we have our equation for T total equals this. And what's our next step? What's our next step here? We're dealing with an optimization problem, right? So whenever you're dealing with the optimization problem, what do you have to do? You have to differentiate and set the derivative equal to 0. So we have to take the derivative of t total, but with respect to what variable? Well, what's really the only variable in this equation that we have here? Really, the only variable is x, okay? You can take, like, because, you can imagine taking a bunch of, different triangles A, or different, A's and different B's. If you just, like, cut off this triangle at, different points, right? But that's not really, relevant to figuring out the answer to the problem. What we want is to take the derivative with respect to x, okay? Because the crux of the problem is really how much time is the light spending in the air versus how much time is the light spending in the water, okay? We're differentiating with respect to x. And, another reason to differentiate with respect to x shows up in both equations, right? That's the variable that we're dealing with, okay? So we're going to take let me do it in black. D of t total with respect to x. And it's just a simple matter of taking a derivative, right? Derivative of a this is the kind of derivative you guys have taken, plenty of times before. So I'll just, get into it. We have, derivative of this is going to be 1 over 2 times 2x times a squared plus x squared to the minus 1 over 2 over v1 plus we have 1 over 2 times b squared plus l minus x squared to the minus 1 over 2. And then we have to take the derivative of this little thing in there. So times 2 times L minus X, and whoop, looks like we're not going to have enough space. Uh-oh. Okay. Times 2 times L minus X, and then finally we do the chain rule one more time, times -1 divided by V2. V2 is just, just a constant, just chilling out there. Let's clean things up a little bit. So then we get x over a squared plus x squared to 1 over 2 times v1 plus L minus, minus, in this case, we're going to have to be dealing with, it's going to be minus because of the negative sign there. L minus x over square root of b squared plus L minus x squared times v2. Okay, and this all equals 0. So we've gotten to this point. At this point, you may be thinking, okay, well, what am I supposed to do with all this, right? We have these really complicated expressions for, after taking the derivative, there's no obvious way to simplify this, but this is where we have to but remember, we're trying to massage this to become this thing, right? So in that spirit, what are we missing from this equation? We're missing the sine thetas, right? So let's figure out what sine theta 1 and sine theta 2 are really quickly. What's sine theta 1 going to be? Well, sine theta 1, sine theta 1, I'm going to bring the picture down here, okay. Sine theta 1 is going to be equal to opposite of our hypotenuse, right? So it's going to be equal to, remember this was x and this was h1, x over h1, which is equal to x over square root of a squared plus x squared, right? And then sine theta 2 is equal to L minus x over h2, which is equal to L minus x over square root of b squared plus L minus x squared. Ta-da! Look, see? This thing is equal to this thing. And this thing is equal to this thing. They match up perfectly, okay? So therefore, we can say that 0 equals sine theta, actually I'll keep the color coding, sine theta 1 over v1 minus sine theta 2 over v2, okay? So then we have sine theta 1 over v1 equals sine theta 2 over v2. And now it's just a simple matter of rearranging, and there we go. Quod eros demonstrandum. We've proven Snell's law. So there you go. It's just an optimization problem. Key takeaway is draw the picture, right? I know I kind of got rid of the picture. Draw the picture. Figure out what you're minimizing with respect to. Try to minimize as many of the variables as you can. And another thing I'd recommend, another good tip, is when you're ever dealing with right angle triangles, look for similar triangles. Write down the sines and maybe cosines of the different angles, and so that you're able to identify them in once you do the minimization. And that's how you do that. Great. Best of luck on your midterm, guys, and make sure to feel free to email me or reach out if you have any more questions. See you around.